own repository or own directory, you can run your own tests basically. So if we run this, we are going to go into BN254 and we can just run the tests. I already have the output from running these tests. Doesn't really matter, but what I want to show is this feature that this line is basically important. It says Icicle backend loaded from whatever directory you had given, which means it has successfully found the GPU, and therefore it can run these tests, or whatever you are trying to run, it can use the GPU for that. If you didn't have a GPU, if you run this exact same command on your local machine, or let's say your laptop where you don't have access to a GPU, then it will just fall back to CPU implementation. So you don't need to like worry about while you are developing with Icicle. You can develop on your local machine. You don't need to worry about having GPU access always. Let's say I'm on a flight, or let's say I'm somewhere I can't use the GPU. I can still do the development, still make sure the tests work, everything works with the CPU, because everything will then just use CPU. And then whenever I have access to GPU, I can just plug in the GPU, plug in this command, this set this environment variable, and then it uses GPU in the backend. So now, so this basically like was a very quick setup, and this is all you need to do when you want to use Icicle or run some tests with an actual GPU. The next thing that we'll do is we'll try to run those entity examples that we saw in the same Google Colab instance, and try to see what we get. Before that, I'll quickly show the okay, I need to connect. I'll quickly show the entity code. Okay, I have it here. So if you let me make it a couple of notch bigger. So if you go in the source Icicle repository, there's a bunch of examples in the examples repository, and we have examples in all three languages: C++, Golang, and Rust. And we have examples that try to replicate the end-to-end process. So in your repository, you can directly sort of integrate Icicle, and there's also example that so this example that my cursor on, install and use Icicle. It's basically like a plug and play thing, how you can use Icicle in your own repository. So the examples that we are interested is these two examples. There's an entity directory, and there's a best practice entity. So entity is basically the naive entity that we saw, and best practice entity is the optimal version that we saw. So I'll not go over the code I'll not go over line by line of what's going on here, but just try to give like a quick overview. So in the naive example, as I said, we are basically doing one operation in our GPU at a time. So that operation can either be entity computation, or it can be data transfer. So so you see on line 49 we are doing the entity computation, and then once where's the data transfer? Yeah, I think we don't have the data transfer being done here, but basically what we are doing here is we are doing a sequential computation. Just simple entity. If you have multiple polynomials, you are computing entity one by one. In the other example, which we discussed a bit earlier, we are doing three things simultaneously, as I showed. We are computing the entity, and then we are also doing the data transfer simultaneously in the same GPU. So we have divided the GPU memory in two parts. One is for data transfer, one is for entity computation. You can also customize how you want to divide the data. Let's say your polynomial size is only requires 10% of GPU memory, so you just use 10% for storing a polynomial. Rest 90% you can decide if you want to load more polynomials at the same time. If you can sort of play around with this trade-off of data transfer and the compute that you want to do in the GPU. Okay, so now let's try and run these two examples in our Google Colab instance. So I'm going to maximize this. Okay, one test fails. I don't know why. Okay, so we are in the let's say where we are. We already have downloaded the repository. We have already set up the CUDA backend. Now we just need to run these two entity tests and see what happens. Oh, test is still running. I'll just pause this. Okay. Okay, so we need to get back. Okay, so we are back in the root where we have the Icicle repository. We'll go inside Icicle slash. Now we want to run this entity test, so we'll go in the examples and then the naive entity. Okay, just check we're in the correct thing. Okay, now we need to we simply just need to run this bash script. So the bash script is basically just uh, checking where the CUDA backend is and checking if you want some more features that you want to run your example with. It's also basically pointing to where the source code is. Typically, like in C++, you need to write this bash script to make it a bit easier to like run tests. But in Rust, it's much easier. You just need to do cargo test, and we'll see the Rust example as well. Okay, so let's. Oh, I should have asked. For those of who you are trying, did you follow these last couple of steps? Content is basically like the root, like the root of your Google Colab. You need to give this percentage sign. No? Sorry? Yeah, you can just pause the test. It takes a while to run all these heavy tests. You found the content? Okay. So if you are in the entity directory, you can basically run this command. Yeah, I should give this. So in the script that we have written, the bash script, we have two like arguments. One is, do you want to use CPU or CUDA? So the first one, we are saying the device we want to use CUDA because we are connected to a Google Colab GPU. And minus B is you need to give the path of where this where you have the backend directory. So as you know, we have downloaded and installed or stored our backend in this CUDA backend directory. We want to run this particular command. So let's see if this works. Yeah, it takes a while to compile. I just scroll up to for people to see the commands. Did you run this command? Yeah. It takes a while to compile because it's doing a fresh compilation, because now it's doing all the computation compilation in the Google Colab server. Okay, looks like it worked. Right, so what we are seeing here is some logs that we printed of the entity, and now in this naive example we are not doing the data transfer. So therefore all you see is the time it took for entity, let's say the radix 2 entity, and then there's a mixed radix optimization that we have implemented that is a bit faster. Um, so now you see that for doing one entity it takes like around 80 milliseconds. This of course depends on the size of your input. It's 1 million currently, 2 power 16 I think. But now what would be interesting is if we run the best practice, the optimal entity example, and before we run it I'll just quickly show like what. So in the previous example we are basically just checking the time it takes to compute an entity on GPU. So that's why it's very fast, it's pretty fast, like just doing the entity. But now when data transfer gets involved, then you'll immediately see that things blow up. Maybe we can do a, maybe we can try and measure the data transfer here itself. I hope this works. Size of entity. What is the block size? Okay, I think it's just one block. Okay, I don't think I can run this in the Google Colab because basically I need to push this to GitHub and then switch to that branch and then run, because Google Colab doesn't know what I'm doing here locally. I'll have to update the Google Colab repo. So I think we should get a fair idea from even running this optimal entity example of what's the time it takes to run the to do the data transfer. So I think these parameters are somewhat similar. I think this was 2 power 20. Okay, and batch size was 2. Okay, that's okay. Okay, so we'll try to run this optimal entity example where we are also doing the data transfer, and we are all obviously also computing the entity. So again, to do that, we'll go back to our Colab. We need to run the exact same command, but inside the so we'll do what's it called, best practice entity. Okay. Okay, so now we are running the other example, and you can see here it tells you that it's using a CUDA backend from a particular path. If you are just not connected to a GPU, it will just fall back to CPU by default. Just bring up the command again. Yeah.
I was looking through the code for your Rust entity. I realized that are we using some C bindings, for example, get file reusability? So in other words, am I right to say that the main so-called CUDA operation is being handled in the C pipeline, and then
Yes.
the binding is being exposed? Okay.
Yes, exactly. So we just expose the API for.
Right. So basically, the bulk of the logic is being done using C.
C++.
Yeah.
Yeah. Okay. So now what you see here in the output is the time it's taking for this entire operation in one single run. So in one single run, you are doing entities. You are doing one entity, and at the same time you are also doing some data transfer. Now you'll see the first two runs, it's the amount of time is like 700 milliseconds, because in the first two iterations, if you remember, most of your time is just copying your first two polynomials, because you can only do parallel computation, but first you at least need to set up two polynomials in your GPU, and only then you can do the parallel computations for the next round. So that's why the first two iterations you see 700 milliseconds, and now you can imagine for the same size the basic entity operation was taking like 80 milliseconds or something, 100 milliseconds, but then now data transfer is overpowering, because 2 power 20 is still like I think a million, if I'm not wrong. So that's still a lot of data that you need to read and write from the device. to host. Yeah.
Sorry, another kind of beginner question. So you mentioned over here that copying the host device and then back again is expensive, right?
Yes.
So when we are performing like a more complex operation, for example, there's a host, where we're able to then use a few operations in the GPU. So what is Iceberg's approach to avoid to reduce the number of like copying device host and back again?
Are you asking, is it possible, or can we somehow reduce like the data transfer?
Somehow reduce the amount of data transfer, maybe by using only a pointer to some memory.
Yes. So it's actually possible, and this is something Icicle also supports, which is you need to do in the beginning and in the end you need to do some data transfer. Okay, you might not need to send all of the witness data, because in snark generation you only might want to like do some operations on GPU. So for example, let's say you only choose to do the MSMs on GPU. So you can only send those polynomials that you are going to commit to the GPU at the start, and then it stays on the GPU. It does all the computation, and whenever, so MSM basically generates a small output. It just generates one field group element. So copying that back to host is easy. So you can employ these kinds of strategies to selectively do some computation on the GPU, and then only copy the data that you need for those operations. So it's actually a pretty good idea when you actually do optimization. So this again like depends on the use case. For example, if you are implementing a Plonk prover, even when you are doing some GPU operation, or let's say you are doing entities on the GPU, you can keep doing some other computation while on the CPU. That's not very heavy, but it still takes time. So you can sort of like split between the CPU and GPU, and also typically what people like want is the ability to be able to use multiple GPUs. Like for example, in Plonk, let's say you have 4 witness polynomials, or let's say like if you take Halo 2, you have hundreds of witness polynomials. Now when you want to commit to all of them, you can basically parallelize all of that. You can do 100 parallel MSMs. For that you need like multi GPU support, and each of them like you can basically distribute them across multiple GPUs, and Icicle supports handling multiple devices, all using one single like interface. I'll show an example after this.
Another kind of question.
Yeah.
What if my GPU is big enough, I have enough memory that I can just use different parts of the GPU and I don't have to distribute it? Does that make sense?
Sorry, ask the question again.
Like, for example, because the GPU itself is memory, right? And it's big, it's kind of big.
Yeah.
So what if my so-called MSM, my hundreds of MSM memory, I don't need to spread across my GPU because my only one GPU is good enough.
Yeah, of course. That optimization is already there built in the backend. I'm saying if it's not enough to use just one single GPU, because one single GPU, you're right, one single GPU is also pretty large enough these days to accommodate like a lot of MSMs. But let's say something like Scroll prover. So Scroll, if I remember, has like thousands of witness polynomials. So in that case, like it becomes imperative to use like multiple GPU instances. So I was basically just summing up this timings that we see here. Then once you enter the third round, you see like 260 milliseconds. So you see like a 3x thing that you pointed out, that you get like a 3x improvement in your end-to-end runtime for doing these things parallelly. I'll quickly show an example of how you can do multiple devices, and then we can probably take a bit of a break, and then we can do some Rust examples if people